Buenas. Hi. Yeah, that's better. All right. Hopefully I'll be able to deal with the microphone properly. Maybe. Anyhow, so my name is Andres, and I'm going to be talking about these lovely things, linked weak reference arrays. Before I start, I'll point out that there's some people to thank here. Specifically Lam Research for sponsoring IWST this year. I presented this paper at IWST, and Lam was sponsoring the paper competition. This paper won second prize. So thank you, Lam, and thank you IWST for allowing me the opportunity to present in this venue in IWST. And now, linked quick reference arrays. As you all know, right? Weak arrays usually have these strong instance variables here in green, and then they have these weak red slots. And what happens with these guys is that, so suppose you have some objects stored in the weak array, and at some point one of those objects is no longer referenced. Well, because it's a weak reference, then the garbage collector comes over and says, oh, that's very nice, but not anymore. And although various other smalltalks tombstone with nil, that is, the reference, this weak reference is blasted away by the GC because the object was no longer referenced. So some smalltalks tombstone, so-called, with nil, but some others tombstone with 0. In this presentation, we'll be tombstoning with 0 mostly. And so the reference in the weak array is blasted away. And eventually the finalization mechanism arranges that the weak array receives the mourn message, indicating the weak array that something has been blasted away in it. And as everybody else knows as well, an ephemeron is kind of a weak array, but it has first off, it's not an index collection like a weak array. It's all, name instance variables. Except the first one typically is pseudo-weak. And pseudo-weak in this sense. So suppose you have, again, an ephemeron, and all the keys in the ephemeron here, whatever is stored in here is referenced. So these are the references coming from some other objects. But the key is not referenced. Well, instead of the key getting blasted away and tombstoned by the garbage collector, what happens is that now the ephemeron becomes a really strong object, and again it's arranged that it receives the mourn message or the finalized message or whatever it is. This should be more or less clear to everybody, I guess, I hope. If not, this is your chance, because what comes next? No questions. Awesome. So, this problem started, as with everything else, with a problem that was a little bit far removed from these considerations of weak arrays and ephemerons. So in GemStone, in the GemStone clients that you have here, right, there has to be a synchronization between what's in the image, in a particular image, and on the server side, here, the server has all the objects, but the client only has some of them, because this thing can be much bigger than what a client can remember. And so the GemStone client has to arrange a relationship between what's in the image and what's in the server to keep track of, this object changed, so when I commit, I have to put it here, or I abort the change, so I have to get a new copy of this object, so I have to replicate it over there, and so on and so on. So how to keep this map? Well, one way would be with ephemerons, right? Because that's great. We could put each of these objects in the pseudo-weak field of the ephemeron, and should this object go away, then this guy will be finalized by the garbage collector, and because this guy mourns, then you realize, I can throw the ephemeron away because this guy was forgotten. But the problem is, suppose now you have a lot of objects. Well, if you have a lot of objects, now you're talking about putting an ephemeron on a per object basis, and now you're talking about for each object, you're going to add another object that has another object header plus random stuff in it, blah, blah, blah. It costs memory. Plus, if you get a bout of finalizations where now you're talking about throwing perhaps several 100,000, a few million ephemerons at the finalization mechanism, and it's not going to work. So another way is to use weak arrays, in which there's like a table of pages, right? And each page is arranged so that each page remembers what happens with a bunch of objects and so on. And when one of these goes away, then the weak array is notified because some slot in there is tombstone, and then it receives more, and then you have to go figure out which one was blasted away. But at least, because you have now one object, one weak array per a bunch of objects, now you're using less memory, and you can amortize the cost of the weak array because, well, now you have less objects on a per object basis. But it causes problems, this weak array business as well, because although ephemerons, right, have the con of costing you more on a per object basis and costing also the VM more overhead, because, hey, so you're talking about finalizing a whole bunch of ephemerons. Well, now that means that you have to have an ephemeron list that can hold all that, a finalization queue that can hold all that, and what happens when the finalization queue overflows, and all the nasty things that happen with that, right? On the other hand, that's great because finalization only costs you, right, the one finalization. So one finalization, one object. So that's great. But with weak arrays, although this is much more efficient space and overhead-wise, however, it has an extra problem because when the VM tombstones something, you have to go find the tombstone, and now you're talking about linear search, and that takes time. And so this talk then starts with the problem of let's try to get rid of linear search in the context of this GemStone client interaction. Now, mind you, we're talking about now a situation in which there's tremendous performance pressure, both on the execution speed side of the house, as well as on the memory efficiency side of the house. So this is not about just getting a better solution. This is like, I need the best thing possible. So one of the first things that happened, and Martin? No, Martin's not here, but Martin McClure and I worked together on this quite a bit. So he said, well, okay, so it so happened to be, the first exposure to this problem I got was that it happened to be that the GemStone client interaction with the server is far more efficient because of its design when it can assume that during an interaction with the server there will be no tombstones in these weak arrays, because of course the ephemeron approach is so memory intensive that you can't use it, so you're forced to use weak arrays. But if you get a random tombstone there at the wrong time, that costs you time and efficiency, because now, all the assumptions that I had about the tombstone not being there, now they are not valid, and consequently I have to go scan again. And what happens if while I'm scanning I get another garbage collect, and then I get another tombstone, and no. So a way in which you could get rid of the tombstones is to make a strong copy, right? Because if you took this weak array and made a strong copy while the interaction lasts, that's okay, because now you have a strong reference to everything, so you cannot tombstone anything, because everything has a strong reference. Well, that's great, but now you copied perhaps several hundred megabytes worth of stuff, which then you will have to garbage collect. And that's not nice. And so a better solution than doing that is, well, it would be nice if that weak array would stop being weak for a while. And that's what I had to work to get going. And that's what I did. So then the same, now not a copy anymore, okay? Now, the same weak array, by sending it this message is weak container colon, you can change it from being weak to strong to weak again. And at first this sounds like, wow, what a big deal. I mean, you just changed a flags in a header somewhere. But you know, if you have an incremental garbage collector and it has seen some objects already, and it has put one of those weak arrays in the weak list, and now you make it strong, what are you going to do? Or even better, suppose you go to the thing and say, right, sorry, so it's now strong again, but now I have to scan it because I didn't scan it before, the poor incremental garbage collector says. So it starts scanning it, and now you make it weak again in the middle of the scan. So what are you going to do, right? Do you put it back into the weak list even though you took it off? Or do you leave it in the weak list because it was in the weak list at some point? And what do you do with this half-scan thing that you did? And on and on. And let's complicate matters. And while in the middle of all this, let's try to really make it robust and play with become, change classes. Okay, it can be done. It can be done. So it can be made to work with ephemerons and weak arrays and all this and change classes and blah, blah. So that's great. Now, this already is nice, right? Because you don't make copies and you prevent tombstones when you don't want them. And you can still leave the garbage collector running because you can't really disable the garbage collector to prevent tombstones, because what if you are really running out of memory and you need to run the garbage collector? So this is great, but it's not enough. The other problem that weak arrays have is, well, the VM is behaving a little bit like a troll here. Because it's basically saying, I'm going to put all those tombstones in there, and I'm not going to tell you where they are. Well, thanks. That's very useful, you know, because just a moment ago where you put the tombstones in there, you really knew where they were. Now you're not telling me. Consequently, when a weak array mourns, it has to do linear search. Right? Want to do blah, blah, blah. If it's 0, then mourn. And this is how it usually is in all these systems. Of course, linear search is bad. So how about, but mind you, I haven't implemented what's going to come next, but I have enough evidence to show that it's good. And that's why I wrote the paper. And hopefully I'll get to implement it soon. So, much better. Well, let's think about this for a moment. So, tombstoning with 0, why tombstone with 0 instead of nil? Well, for one, because when you do a weak array new, right, all the slots get initialized to nil, so immediately if you were tombstoning with nil, you do not know if that nil that you're looking at is because there was nothing there or something at tombstone. So tombstoning with nil, not such a great idea. That's bad for hash collections because you could imagine that if you wanted a free slot and, you know, now you're looking for nil, but is nil really an empty slot, or is it the middle of a chain that now could have been broken? So, right? And so you could tombstone with 0. Well, why? Because 0 being a small integer, well, obviously if you put a small integer in a weak array, the small integer being immediate, it can never be garbage collected, so it can never be tombstone. So if you find an immediate in a weak array, it must be because the VM put it there. So that's how you can distinguish it from other things. Well, but if you can tombstone with 0, you can tombstone with other things, such as, for instance, this. Let's put a linked list of tombstones, in which the first instance variable of now linked with weak array, points to the first slot of the list of tombstones, and this one points to the next one, and so on until you find the 0, which signals the end of the chain. Well, great, because now I know where they are. So thank you just saved me from doing linear search. Now, obviously, mourn is very similar to the previous mourn. Get me the next one, and as long as it's not 0, then mourn and that index, and then the next tombstone is whatever is stored at that index, right? So this one starts with 6 in this case, and this one takes the values 12, 15, and then 0, and then the loop exits, right? Now that's very nice, but I'm sure you're now thinking, well, I'm sure you can break that. because that code assumes that this little boxed section is atomic. That is, that there will not be another garbage collect in the middle of this and blast me the head of the linked list and put something else in there, say a 0, meaning, well, there were no more tombstones or whatever, right? So now this then has to become an atomic section. You can't have basically another tombstoning pass until you finish mourning that one. So how do you deal with that? Well, sure, you could put a semaphore, you could put another instance variable that has another small integer that indicates, or you could make one negative and be smart and say, because if it's less than 0, and then you still always have the problem of, well, did a garbage collect happen right after you made something negative, and then you don't see it, and then you do the wrong thing, and da-da-da. What a pain, right? Let's make it better. So, if you recall, ephemerons, when they mourn, they become strong. So, for linked weak arrays, this is a way to avoid all the synchronization problem. When they mourn, the VM itself makes them strong. Makes them strong, right? And now they are strong, and because they are strong, there cannot be any more tombstones. And so if the VM will leave my linked list of tombstones alone until mourn finishes, at which point the last thing is, hey, and make it weak again. And now I'm ready for the next one. There, no more synchronization problems anymore. And no linear search. That's the core of the idea. Now, what else could one do with this? Well, another thing that one could do with this is that each time this thing runs, right, it gives me a linked list of tombstone slots, which, say, in the context of implementing a weak hash collection, means that every time this thing runs, it gives me a linked list of free slots. Well, during mourning, then, I could just link the two chains and keep my piling up, my nice list of free slots, which I then don't have to find either, because I always know where there's a free slot. And if I don't have anything, then I know there's nothing. How many times have you looked at how a, say, symbol table is implemented? Well, if you were looking at how a symbol table is implemented, then typically you'll find that there's weak arrays that hash bucket all the symbols. And as the symbols get collected because they're weak arrays, now there's a 0 in there. And then you have to find the zeros where you add a new symbol. Right? But this, bye, no more linear search. And that's nice. And there's, of course, other applications and so on. So, any questions so far? Or is this clear? Sounds like it's clear, right? Simple idea, right? Okay, so there's more to it than this. Well, obviously it's faster, right? Because obviously here, right? Here you can see these are the tombstoning rates for several sizes of arrays. And so basically I simulated what would happen if I were tombstoning this from the VM, and see how fast mourn would go by comparing the code that the two methods that I showed you, right? The mourn for weak array versus the mourn of the linked weak array, in which there's a linked list of tombstones. And obviously, right, so let's say, for a tombstone rate of 10, meaning 1 every 10 slots is tombstoned, then sure, the thing starts running 10 times faster. Right? Because over there, 10 times whatever, right? But interestingly, even when the collection was small, even when the collection had only 1 slot, still it was 30% faster. Because of no to-do. Because of no checking whether the thing is small, whether the thing is a tombstone. Because you already know. If you have the index, then you know it's a tombstone. You don't have to ask questions anymore. Right? Because the mere fact that you find a non-zero tombstone index tells you the next thing you find, you need to mourn. You don't need to ask anymore. Right? So that was surprising that even in the case where you would expect performance to be the same, linked weak arrays are still faster anyway. And of course, even with larger collections, you get the speed up that you would imagine. As the tombstoning rate grows, the logarithm of the speed up grows linearly like one would expect, because the tombstoning rates are exponential as well. So really, that's the story. Do you have any questions? No questions. Great, thank you.